Hi everybody, my name is Paul Day, and I'm going to quickly go over the results of a study that we did in 2006 and finally released in publication form in the form of my thesis in 2012 on the geology and seismic potential of the Hustain Fault in central Mongolia. I want to quickly mention my collaborators, Tom Kelty, also at California State University at Long Beach, and Batulzi Dash at the Mongolian University of Science and Technology. The purpose of this project was to go out and map what was ultimately a very poorly studied fault located very close to a central population area. It's an economically important area, and we really needed to know something about it. But there's kind of a more academic reason to understand. What is the role of this fault and this structure in the overall scheme of Asia? And can it give us a good idea for what other faults in the area might be doing? And we think that we actually got some good information on it, at least as a start for other areas that we could study in Mongolia. So with that said, I want to quickly go through, it's about 45 slides of information. Hopefully it will be useful. These are the highlights of the thesis. Incidentally, the thesis will be posted, or at least a link to the PDF of the thesis will be posted in the comment section down below this video on YouTube. So if you click there, you can get a free download of it. Okay. And the background image that we see here, we actually see the Hustain Fault. This is one of the nicer exposures of it. We see a nice shoulder slope coming down, and then we see it definitely with an escarpment intercepting the landscape right here, and then nice kind of colluvium covering along the base of it. The exposure of the fault was not always real good, but there were places we were able to get really good measurements and see clearly what was going on. And I think that this talk will be enlightening. So let's go on to a couple of comments from the thesis and why we were so interested in this. Well, Mongolia, this is actually straight from the thesis, so I'm going to go ahead and put this in. These are really important points. Mongolia has endured 4 magnitude 8 earthquakes since 1900. And this is very unusual. Mongolia is a long distance away from any tectonic plate boundaries. This is not what you would expect. Right? All the large earthquakes tend to happen out on the edge of the continents, not in the center of these continents. And of course, Mongolia is one of those places that could be said to be as far away from the edge of a continent as you possibly can get. And of course, at the time this study was conducted, very little was known about the seismic potential of many of the faults surrounding Ulaanbaatar, which, according to 2013 estimates, swells to over 1.31 million permanent residents year-round. So this is a very large city. It's a very rapidly growing city. The economy is booming there. Construction has boomed there in the past, and I haven't been there in a while, but I'm sure that the city is starting to sprawl and to really build itself up. The geology of the region is very complex. It's located directly between the active Himalayan mountains to the south and rifting Lake Baikal region to the north. These seem to be kind of, a area of compression from the south and an area of extension up to the north. And something weird seems to be happening through the area. We wanted to see if we could figure out some keys to this. And so Mongolia is right in the middle of this, and it might be the key to unraveling a lot of that complicated geology found all the way throughout Asia. Here's a photograph I found online from a Russian website of the 1967, I believe it's pronounced the Bogd earthquake. Here's the fault rupture. Here are 2 people standing on the rupture, and here we can see what we call mole tracks of the fault moving off into the distance. So this was a sizable earthquake, and if something like this was to happen anywhere near Ulaanbaatar, very, very, very bad things could happen. So we were interested in looking at what was the biggest, most obvious, and most unstudied fault right next to Ulaanbaatar. So the Hustain Fault is one of the best exposed faults located in a relatively unstudied yet heavily populated seismic zone surrounding Ulaanbaatar. That's what I just said. The fault presents an opportunity to study the broader region as it could serve as a proxy for the movement of other nearby yet unstudied fault systems. Therefore, the purpose of this investigation was twofold. One, to determine the geological relationships of rocks located along the Hustain Fault to acquire insights into the tectonic history of the area. And two, to determine the seismic potential threat posed by the fault to Ulaanbaatar. And so here we actually see a photograph I took when I was in the field. This is the fault surface, part of the Scarp anyway, well exposed. We got very good data off of these types of outcrops all along here, and we were able to get a very good understanding of the answers to these questions that are being posed in this study. So we're going to go ahead and go through the data that we received and looked at. So the first thing we have to ask is, where is the study area? What is it that we're looking at? Well, here's the geopolitical outline of Mongolia. These are the main geographic features that are relevant to the study area. Lake Baikal is up here to the north. The Hentay Mountains just north of Mongolia, or I'm sorry, of Ulaanbaatar. They actually extend into our field area. The Hustain Mountains are considered part of the Hentay Mountains. The Mongolian steppe region, the Gobi Desert, here's Beijing, the Hangay Mountains off to the west, and of course the Valley of the Lakes and the Altai Mountains are off to the west. The areas that we're going to be focusing on are things right in here. Another couple of important things to bring up are the areas that we think might have important tectonic consequences for what is happening in the region around Ulaanbaatar. The Angara Promontory is located right here, and we could, as we go up and we map this area, the results are that we have a series of thrust sheets that exist over here to the west, and a lot of rifting over here off to the east of the Angara Promontory. We see these same kinds of structures extending down into Mongolia this way, and I suspect we're finding the same thing headed down towards Ulaanbaatar from the Baikal Rift Zone. Down to the south is the East Gobi Shear Zone. There's a lot of good geology being done and published down here, and I think that we're seeing, in essence, the combination of all three of these regimes occurring right between the Hangay Mountains and the Hentay Mountains. And I think there's a lot of really good stuff to go out and learn that's still out there, not found yet. These are the positions of major earthquakes that have happened in Mongolia since 1900s. Magnitude 8 and larger are marked in red. Those that are other major earthquakes, maybe not quite magnitude 8s that have happened since, have happened here. I believe this is the Darin earthquake, and this is the Bogd earthquake located over here to the west. So here's Ulaanbaatar. Ulaanbaatar, you'll notice that most of the earthquakes are happening to the west, and it seems like there's a seismically quiet zone over here off to the east. The explanations for this range, and I will possibly have time to get into it in this talk. If not, it's definitely covered in the thesis. So our study area was located at about a 45-degree angle from north, striking right down into what we call the Tuul River Valley. So here's the tectonic map of Mongolia. This is from Tom Kelty's and his collaborators' paper from 2008. This is here we see the Hentay Basin, the Hangay Basin here, and we have these regions of rocks that are kind of wrapped around here, and we'll come into why this is argued by some according to some geotectonic models, but Arch in particular seems to like this idea of rocks being wrapped around the Hangay-Hentay Basin through a back arc basin. So our study area turns out is located right here. So here's our study area, arrows pointing right into here, and if you get the chance, this is a good paper to read on the geology around Ulaanbaatar. So the basin closure models are really important to understand. At least this is kind of our framework going into the study, was that there was this series of basically rotations. Here we have Sangor and his collaborators from 1993 showing the folding of the Tuva Mongolian block with subduction zones on both sides, and as they scissored close, you wind up getting a Hangay-Hentay basin forming in the middle. Zorin's 1993 paper shows that this is probably due to a collision with Siberia. You might have actually had some uplift or an orogenic event right along Siberia. as the Mongolian block slams into it, and then it folds with time. Again, in this case, instead of having two subduction zones, he has one south-dipping subduction zone that's accommodating that folding and that rotation. The Badarch paper of 2002 interprets this as a back arc basin. This is a very well-known paper, and it was one of the papers that I kind of based a lot of my ideas on early on. There's, in my judgment, based upon some of the evidence, some things that can be refined from these ideas, and I'm sure that Tom Kelty's new ideas are basically building off of these old ones and improving upon them based upon new data. But this was kind of the model I had in mind when I went out into the field originally. And so as these models all have one thing in common. It's the fact that we're seeing these blocks close together in a scissor-like motion. Again, these two have in common the south-dipping subduction zone and all of that. I think that there's definitely some problems here, that the geology doesn't bear this out, but I think with time we're going to start to be able to refine these ideas and to get a better idea of what kind of basin the Hangei-Hentei Basin actually is. I don't know that at this moment, at least at the time that I went and did this research, that we had a firm handle on that. So this diagram down here by Krevchinsky et al. In 2008, I think does a really good job of showing the positions of something called the Stitch Complex. So the Hangei-Hentei Basin extends between these two granitic basements, as we're seeing here, and intruding throughout it, we have a whole series of plutons. They seem to go from Cretaceous in age, and they young as we go to the east all the way to the ocean, along a series of what is sometimes interpreted as strike-slip faults, and sometimes they're interpreted as thrust faults. We're going to come into what our findings were in our Tuul River Valley, which was located right over here. This is our study area where we actually had a very nice Triassic age granite. But the idea being that there's these granites that are aging or younging as we go to the east is kind of an important concept here. So we were mapping right in the region of one of these. So another very important piece of data that we had going into our field investigation of the Hustain Fault was that we had GPS measurements. We actually knew the recorded motion of different areas, all relative, I believe in this case, to Irkutsk, which is located in this image up here to the north. I believe that's what they were using as their standard. And when we look at this, we recognize very rapidly that the areas off to the west have a very large northeasterly vector pushing up towards the Angara promontory, which is located right up over here. And as we move from west to east, we notice that the trajectory of these arrows, the strike of these arrows, go from more northerly to more easterly. And then when we get over here into the eastern part of the country of Mongolia, we find that we start seeing trajectories of east by southeast. In fact, here's the Hustain Fault as it's mapped on this image, and I've marked it with a red circle. Ulaanbaatar is moving at about a 4.6 millimeter per year clip to the east by southeast. There is a caveat though, and that is that research by Eric Calais and his collaborators suggests that we might need to incorporate a correction when we look at these data. So here's Eric Calais' map. This is actually modified from Eric Calais because I've got this marking TRV stands for the Tuul River Valley. This is where we're going to be doing where we did our field study. And what he recognized is that while the official GPS shows that we are moving off to the east, he was suggesting that a proper vector would be to the more south by southeast. This is very interesting for lots of reasons that we'll come into later on, but this will wind up matching a lot of the data we find from the fault. So Eric Calais' idea is that there's a large degree of post-seismic stress changes. In other words, the whole stress regime of Mongolia has been altered from the 1905 Bolnai and Setserlig earthquakes. his paper published in 2002 is a must-read for anybody that is interested in trying to coordinate the movement of faults with what we might be seeing in the region around Ulaanbaatar. This is a very important paper to read. So with that said, here we see it here. This gives it a more south by southeasterly vector, and as we will find by the end of the talk, that this is corroborated by the data that we discovered as well. So let's bring up a couple of important features and landmarks, because the area that we studied was so large that if we don't get some, some landmarks in mind as to where they are, it's very easy to get lost on the fault during the talk. So here we see the Hustain range. It's a mountain range. It's not a very tall mountain range. You can easily climb them and hike around on them. To the north is the Loon Valley, which parallels the Tuul River Valley, which is located right over here. Ulaanbaatar is located right over here to the east, and Bogd Khaan Mountain, of course, is located just south of the city. A little settlement called Truncated is located right over here, and I only bring it up in passing because it is so small that it hardly occurs on any permanent maps. We found it as a very small settlement with about 3 gers and some grazers, some animals and things like this, some ranchers actually out there working. But we would name part of the fault system after it, so I thought I would bring it up. The area that we see in the floodplain right down here is a meandering stream system that we now call the Tuul River. The Tuul River is right here. It's used for all kinds of commerce. We believe that this is kind of a key part to the whole story. The Tuul River is actually telling us an important part of the activity of the fault. And so the fault itself is located right along the edge of the Hustain range, separating the Tuul River from the mountain range to the northwest. So kind of in passing, I just want to mention that here's Loon located up here. The Hustain fault is located right along this red zone right here. There's a splay of the fault that we call the Teriot splay that moves off to the southwest. And another important structure, which was much less studied, moves right off the fault. We think it accommodates a lot of the fault motion out of this area and to the south of Ulaanbaatar. It's an important structure, but it wasn't studied enough due to our limited time and resources. But it's been brought to my attention that Mongolia is building a major international airport right along one of these fault splays, and so I'm pleased to present what little information I was able to capture on it. I would like to go back out and do some more work if I can, but it's definitely an important fault trace that's connecting the Hustain fault with structures to the south of Bogd Khaan Mountain, which is located here. And of course, here's Ulaanbaatar, and the old airport is located right here. This is a very large area. This is 50 kilometers, and the study area was largely confined within this dashed area. The stratigraphy is not complete. We have a good understanding of the age of the rocks, but in terms of the details of the sedimentary history, the metamorphic history, and all of this, we still have a patchy understanding. And of course, it doesn't help that there are huge unconformities. There's Paleozoic rocks of the Mandel series, which are Devonian in age, and that moves up into the Gorhi group of Devonian and Carboniferous metasediments and marine sedimentary rocks. These are very thick sequences that make up the Hangei Basin. And then we have a granite intrusion that's in the area, a series of dikes that we interpret as being Jurassic, but could also be Cretaceous. But who really knows? I don't actually have a firm date on it. Just know that it's younger than or I believe that it's younger than the granite. We have a dike swarm that we think is Cretaceous, but it could also be Triassic. It's apolitic in composition. And aside from that, we have a huge unconformity all the way to the late Tertiary, and then, of course, the Quaternary sediments on top. So we don't see a whole lot of neogenic sediments in the area to be able to really tie things together. We see very old rocks, all exposed in a large area, and then we see faulting between the two of them with big alluvial aprons over big sections of it. So there were challenges we had to deal with, and sometimes you just had to use old school geology, rock hammers, and not the high-tech stuff, but the old school stuff to be able to go out and answer some of these questions. And that's what we sought out to do. Before we went out there, we did a lot of remote sensing just to see if we can make an argument whether or not the fault was definitely active or not. And even before we left, we saw telltale signs that the fault was definitely active. Here we can see a clear escarpment moving along here. This is in a what we call a visible 321, which is a true color image. This is what it really looks like. We see a vegetated tributary. We see floodplain that is light gray, and it's of course a meandering stream of the active Tuul River channels. Whenever you have meandering streams in mountains, that usually means that the stream is located below its base level. So it's being lowered below where it's stable. This is kind of a telltale sign of fault activity just in the river itself. Clear shoulder scarp truncations and flat irons located down over here. Very thick alluvial fill located in here, and we can clearly see several fault scarps located through here, as well as a vegetated tributary that comes into the Tuul River, which is probably due to extensional faulting to the south of Bogd Khaan. So just right in the visible spectrum, we can see classic examples of active faulting in the area. When we went to a false color image, this is a standard 742 Landsat, we could actually see the formations. The Altan Uvu formation, which is a Devonian into Cretaceous unit, a Cretaceous unit, is very clearly marked in purple. We can see it, it's clear, it's got this mottled purple color, and we can actually map it. Over here we see this big white plug located along the fault, and we know from geologic maps that this was a granite that had been mapped in the area in the past. And so we knew that this was a granite, and we could map that granite using remote sensing. And then of course we see the Gorhi formation, which was in brown. Turns out there's another pluton located up over here with a strong alteration zone. And when we got into the upper elevations, up high, say up here in Bogd Khaan, it was a little bit more difficult because it's highly vegetated. But again, we can clearly see the Altan Uvu versus the the Gorhi formation, which is this more brown. And of course, we have these variable colors and the intervening formation. So there was a lot of information we could get just from remote sensing. We also did a kind of a cool ratio image, which allowed us to be able to look where water was located, where iron was located, and where silica was located. In doing this, we were able to map out the locations of groundwater springs. And so here we have a spring or shallow water source located along the fault. Here's another one located along the fault. And we interpreted these as disruptions in the alluvium. And this is a clear case of when you have disrupted quaternary alluvium along a fault, we interpret that as an active fault. There's no other way to really interpret that. The other thing that's really kind of neat about this is you can clearly see the difference between the rocks of the Cretaceous and those of the Devonian, located right along here. And here in the green, we see that granite plug again, showing that it is slightly different. So there was a lot that we could get just from looking at the satellite images. We learned a ton just right there. So we subdivided the whole area. Remember, we're talking about an area that's over 100 kilometers in length by about 40 kilometers in height. It's a very large area. We had to break it up. And so we broke it up into, the western sub-area over here with Terriot off to the south, an area called the Haystack Buttes sub-area. We'll be explaining why we called it that when the time comes. The Stepover area. The eastern field sub-area is located up here. Of course, the Tuul River and adjacent hills area is this area down to the south of the Tuul River. And finally, the Bogd Khaan sub-area, which is where, unfortunately, we spent the least amount of time. We were spending most of our time on the main fault trace studying it. But we did get a little bit of work over here, and we were able to come to some preliminary conclusions on what was happening there as well. So we'll show you the images that we got. So this is the western sub-area, and when we looked at this, we saw some really interesting things. A lot of these rocks here had been mismapped in the past, so we had to actually disregard some of the early maps that we'd found and remap it. When we went out and actually saw the rocks, we realized that what we were seeing in the satellite images could be verified. So we actually verified a lot of this. So here we see the fault along the south extending. Unfortunately, in the original image, this is a dotted or buried fault trace. It's not intentionally solid like this, implying that it's buried in the alluvium, and that we actually see splays of the fault spinning off into the corner and creating left lateral strike slip structures, or what we interpret as left lateral strike slip structures. We have the linearly faceted shoulder slopes, which are these flat irons that we see along here. We're going to come to this here in a minute, because we actually think that we see the Hustain fault cutting across here and disrupting drainages in this area, very young disruptions. So let's show that here in a moment. So here we see that area in E, this area here in E, located right here. And here if we follow this shoulder slope, we see it's truncated, it's picked up over here. The fault definitely comes through here. And we think that we see a nice left lateral offset along here. We see rapid headward erosion here, and we see a stream capture and an underfit and overfit channel relationship. This is actually described a lot in the thesis, so I don't want to belabor the point, but this is kind of a typical disruption that we see in one of these valleys. Over here to the left, this is something that we had to wrestle with for a while, because a lot of the early maps had striking beds moving through here, and when we go back to the original image, you can see these white images come through here. But when you look at the right remote sensing image, in this case this is a Landsat, well, notice that these come out in white in this color regime, and then crossing them are these ribbons of yellow. And this was interpreted as bedding being crossed by a series of dikes. And in fact, when we went into the field, we were able to confirm that this is the case. And so here we see those dikes, those apolitic dikes, cutting across the surface of the geology of these low hills. Here's cattle for scale out here. And then if you look right back here, these are outcrops, usually cherty outcrops or sandstone outcrops in the hills. And you can see that they're clearly being cut by the dikes. So the dikes are much younger. So here again, just kind of reemphasize this point. Here are the dikes coming through here. And so this kind of corrects a lot of the existing maps that existed at that time. The next area up, we saw that splay coming through here, is the Haystack Buttes area. This is something that Tom came up with. He called it the Haystack Buttes because the granites actually look like stacked bales of hay, and I'll show you a picture of that a little bit later. It's a really kind of neat area to work. And this is a aster image that we used, taking ratios of thermal characteristics of the rocks, and sure enough, the Devonian footwall rocks, as they'll later be shown to be, are disrupted here by this red and yellow zone right here. This is the Pluton located right here, and these are the metasedimentary rocks of Devonian age located right along here. And then you'll also notice that there's a yellow zone right here. These rocks here have a thermal signature similar to the rocks here. And in fact, when we went into the field, we determined that these are both granites. That this is in fact granite located over here, right adjacent to the Tuul River, flowing right through the middle of the valley. And so here we actually see an interpretation of this. Here we see the Triassic granite. Here we see the Devonian Mandel series rocks located here. And right here we find clear Triassic granite blocks located, almost rafted away with an apron of alluvium and grus, actually broken, busted up granite particles washing all over this area right here between the two. But this is definitely an outcrop of granitic blocks that is right up against the river. Very interesting. A couple things to observe about this is that we notice that there's a little block, a little kind of piece of Devonian rocks sitting on top of the granite right at this position. It stands out very prominently from the road as you're driving through here. You can look up and you can see it. It's definitely a place worthwhile to check out. It's one of the clearest places you're going to get an image of the fault where you can actually put your finger right on it. And I'll show you a picture of it a little bit later on. Over here, we notice that the same rocks, these Devonian rocks of the Mandel series, were mapping as an intrusive contact with the granite. But we don't really know for sure. This is actually kind of a speculation on my part from this. It could just as well be that there's a fault. So this is a place where we see clear Mandel series rocks in fault contact with the granite, but we're not interpreting that over here. But that doesn't mean that it's not so. So let me show you an image of what I'm talking about here. So here we see this big field. This is two images I put together of grooves coming off of that granite. The granite weathers easily. It makes these nice little fluvial cuts that we see dissecting the landscape. It's nice and smooth. And up here we see those nice hard metasediments of the Mandel series up on top. And the contact seems to run right along these two rocks right here. Okay, this is a nice flat contact. Is that a fault contact? Is it a roof pendant? We weren't able to make the determination in the limited amount of time we were out there. But that would be something that surely should be looked at or investigated. One of the issues that we had was that there was so much colluvium covering this, it was really hard to find a definitive spot where you can put your finger right on the contact between these two rocks. So this would be something that should definitely be looked at in the future. But back to this original image, we clearly see the fault here. We might see it over here, perhaps even up over here, or it might just be an intrusive contact that needs to be verified. Blocks of granite over here. The other thing that's kind of interesting about this is we interpret two faults located between here and here, probably co-located or correlated faults, maybe splays of one another, and certainly one located out here in the right between the granite blocks and the Tuul River. This is kind of an important structural relationship because it's possible we're having conjugate extensional fault systems working through this area here. And we'll show this in the cross-section, which we take right through here a little bit later on. Also notice that these blocks are slightly offset to the east from the main block over here. This implies a left lateral offset on the fault, but it's not a very large offset based upon what we're seeing here. Okay, so we'll come back to that in a minute. And so here we see those beautiful granites weathering down, and they formed almost these blocks of what Tom Kelty had described as stacks of hay, like you would see on a farm. So that's why we call it the Haystack Buttes sub-area. And for scale, here's our field vehicle driven by our fearless Mongolian student driver who could do amazing things with that truck. All right, so the next area to the east is an extremely important area for working out the kinematics of this fault, whether it was an extensional fault, whether it was a left lateral strike slip fault, a right lateral strike slip fault. And one of the things that we noticed right away in the satellite imagery was that there was this interesting step over on the fault. The main fault trace extended along the base of the mountains, came up, and then suddenly we found that there was a splay that came off and kind of dies back here. We definitely see a sinisterly, you can actually see it here in the image, deflected stream, but then we lose it off here to the left. But for sure the fault has another connection that moves along here. We have disrupted groundwater, another zone of disrupted groundwater. There's an amazing dike exposure located here that was putting all kinds of rocks and debris that were very distinctive into the colluvium and into the alluvium down below. And some of that stuff was offset. In fact, we found a rockfall that was clearly offset from this position that I'll be describing a little bit later. And again, another disrupted groundwater. So we're finding disrupted groundwater here, 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 offset rockfalls here. We're finding a pull apart here, and the interpretation that we get from this is going to be a left lateral strike slip fault. We also interpreted that there was a buried fault structure possibly located out here because we're seeing additional disrupted groundwater in certain areas of this alluvium under different images that we're using. Again, here we can see those very nice meanders of the below base level Tuul River just to the south. And here we have an image. This is an image I took while in the field. I'm standing up on the shoulder slope. I'll actually put my thing. I was standing about right here, and I took a picture pointed down the valley up to the northeast. And so we're up here, and here you can clearly see the fault scarp coming in right behind us and then coming back around on the hill. So this is an area that I wish that I had more time. Oops. This was an area that I wish I had more time to study and get better measurements off of, but there's classical geology that can be done here and studied. All right. The next area here was kind of one of the first areas I interpreted and is easily the most difficult. So here we see those two faults that I had interpreted coming out of the step-over area. Here's the step-over area here. A series of faults paralleling into the main portion or the center part of this image. Here we have the Mandel series. And the Altanuvu in this case comes off as this mottled purple and gold color. Different beds in here. We also found some Cenozoic deposits. Did not have time to study. Again, the area was too large and we didn't have enough time. I wish I could go back and get that done for sure, because I think there's some really interesting stuff to dig out of here. But with that said, we were able to clearly follow the fault because there's some amazing intrusions, some dike intrusions that came along the fault, right on the side of this valley and right on the side of this valley, these shoulder slopes that cut across. And they have great kinematic indicators marked all over them, Tuul marks, all kinds of stuff we're checking out. And as well as disrupted groundwater in here. In fact, there was a wonderful groundwater well that was still being used by people located right about here where the fault was crossing. The early interpretation that we used in the thesis was that this was actually a fault block, almost kind of spun into the area in a left lateral fashion, that the fault had basically cut into its own sediments over here, leaving a small little kind of portion of itself plastered to the south. Later on, I would reinterpret this as a different kind of structure, because when we look at these gold and purple beds, and when we look at the actual dip and strike measurement, or strike and dip measurements from the field, we recognize that this area here is extremely folded, bent up material, and probably faults don't explain it best. It's probably better explained as a giant nap, as a series of nap structures perhaps even. So we'll see that on the final map. Again, here you can clearly see the Tuul River meandering off here to the south. We did some topography on the area. We recognize that we find these nice trellis drainages moving from the highland areas, usually all the way down to the south of the range. So the highest parts are the southernmost parts of the range, and then they shallow out. And then they're very steep on the southern facing slopes. Very steep over here again, very steep over here, again over here. But then they go shallow. Nice trellis drainage patterns over here. We do actually see nice dendritic patterns though as well. One section is here, another section is right along the ridge lines, right? And so this is something that we took as evidence that the faults are moving like this, that they're just kind of rotating and pulling apart at the same time, that you get near vertical uplift creating your dendritic drainage right along the top of the Hustain range, which is going to be a young geomorphic feature. And those trellis drainages are going to be draining, in this case, most of that up to the north into the Loon Valley, not down into the Tuul. The Tuul River is going to be getting most of its surface runoff from the south along the southern flanks of these hills here. So you get that again when you take your blocks and you fault them and you extend them. Here's your trellis, and then over here is your dendritic drainage pattern. And so here we see exactly this. This is an oblique view of the topography from basically right above Ulaanbaatar, looking down to the southwest. Here we can see those nice trellis patterns, those linear valleys moving out into the Tuul River, and the dendritic pattern that looks like veins along the tops of these mountains. And so as a consequence, we get water coming in this way, but as we lift these mountains up, we would expect there to be a large amount of sediment, a huge sedimentary apron, pushing the river to the west, and in fact, or in this case to the south, which is what I meant to say a moment ago. So let's bring this up. We find our disrupted springs right here. So we find springs located here. We actually found 4 of them, so there's another one located up over here as well. And so the final interpretation is that we have an alluvial apron that is the result of the rapid uplift of the Hustain mountain located here. Here's the up, here's the down, and we form something called a bahada, these interwoven alluvial fans that are coming through and covering very rapidly the northern portion of the Tuul River Valley and forcing the stream down to the south to hug the trellis drainage pattern along the southern portion of that valley. And then, of course, it repeats over here. These red dots are the rotational axes, where I kind of believe, based upon a couple of minor experiments I did in my office, where I think those axes would be for rotation. So they're rotating and they're pulling away. That's the general idea that we see here. We were able to put together a generalized geologic map of the area. This is a 1 to 100,000 map. It would be nice to actually have mapped it at 1 to 50,000 and maybe eventually at 1 to 25,000, but this is the best we have. And what we found is that we could clearly demark where the Devonian Mandel series rocks are and where we get into the Carboniferous, Devonian to Carboniferous back arc basin rocks that Bogd was describing. Here we see those dikes intruding down here to the southwest. The granite is located here, the alluvial apron, with the granitic block being faulted off, right? We're interpreting a fault here. And these blue zones right here each represent areas of extreme disrupted groundwater. So this is an area that we interpret as extremely active faulting in the alluvium as well as along the basement rocks throughout here. The fact that the Tuul River is below its base level suggests that it is being dropped faster than it's able to feed the sediment in from the north. And so there's this competition between the sediments coming in and choking the river, trying to get it up to base level, and the tectonics that are constantly dropping the river faster than it can infill itself. It's kind of a neat idea. Over here to the east, we actually measured tensional veins, showing that this area here has separated. It's actually rifted itself apart from this section of the fault here. We'll be showing images of some of these rocks here. And instead of a fault, as I had shown in one of the earlier images, we've got a nappe structure, which I think is Paleozoic in origin. It's very, very old and is probably related to the closure of the Paleo-Asian Ocean during the Paleozoic time period in this region. So it's kind of a cool map. And you'll notice up here we see buried a major structure that then goes off. And unfortunately, the airport would be located just off the side of this map. So generalized cross-section, there's nothing secret here. This is kind of the idea is that this is a standard extensional fault system with a very deep décollement located underneath the structure, that we have a nice Triassic granite that's faulted in, and we see conjugate faults working through here. This is, by the way, where we find this cross section located through here. So here we see the fault here and the fault here and the third fault located there. And this is where we see it manifesting itself at the surface. One, of course, buried with the Tuul River alluvial deposits over here. So these are kind of standard ideas. I believe that it's the décollement is rooted to the south, and that it's probably a major extensional zone that extends all the way from Lake Baikal well to the south, as far as, who knows, perhaps all the way to the Gobi. I think a lot more mapping has to be done to really get some understanding of this. But it's a huge, thick fill that goes all the way down to the décollement. And below that, we're finding the Paleozoic island arc rocks of Zoran and his collaborators from 2002. That's another great paper to read for understanding my ideas. All right. So the Bogd Khaan sub-area, this was one where we had some ideas. Here we see the old airport, Ulaanbaatar is located here. Here, what's kind of interesting is the Hustain fault, we know continues off to the northeast, but it goes inactive. And we see that there's a structural relationship between the Devonian into Carboniferous age metasediments and sedimentary rocks, basically the back arc sediments, and we see the Mandel series footwall sediments. They're right next to each other in a thrust fault fashion, but the problem that we see here is that we don't see any active faulting. We don't know where the active fault structure goes. We don't see it down over here, but we definitely see that there's a series of active fault structures probably down over here. We see the disrupted groundwater. Here we see again that vegetated lowland that has got meandering streams moving through it. This is where the new airport is going, right approximately here. So this is something that needs to be looked at very strongly. We believe there's another extensional fault structure moving off here, striking down to the southwest and paralleling the Hustain fault, and in fact is probably related to it in terms of the general structure of the area, right? It's just another fault of that ilk. We also saw that there was an extensional fault to the northwest of Bogd Khaan, and of course Bogd Khaan has a huge plug of granite in it, so that makes it a very hard and stable section of that region. So a lot of the faults seem to be kind of going around it and accommodating that strength and cutting through the much softer metasedimentary rocks. So really quickly, want to go over some field photographs of the Hustain Fault Scarp. It's a very clear scarp as we showed in the original image, but here we see the hills in the background with a nice alluvial cover. The alluvial cover is usually covered with grass itself, making the looking and seeing the actual class a little bit difficult, but you can see from the geomorphology. Now here we have a captured drainage. There's a feeder canyon over here that goes nowhere, and here's a beheaded channel. This suggests a left lateral strike slip motion. Another beheaded alluvial fan, the original source probably being up over here. So, if you reconstruct this to this over here and this to this, you get a left lateral motion. Again, here we see these obvious scarps moving along the base of the mountains, the shoulder slopes being cut very distinctively, and then even at a further distance out, we can see this area right here. We can see it clearly fronting this entire range of mountains. So it's a very obvious fault scarp that you can see. Here's some more images where the fault is co-located where dikes. So there was a dike or a series of dikes that intruded along the fault surface during the Mesozoic at some point, and we interpret these as anywhere between Triassic and Cretaceous. It depends on who I was talking to that day, but the clear consensus is that they're Mesozoic and possibly Cretaceous in age. If somebody has a reference that can give me a date on it, I'd be happy to take that reference and incorporate it into my research. But here we see these are very large structures. Here's that dike sticking up along the fault, so it has this nice flat iron structure. Here we see it again. This is taken by Tom Kelty, an oblique image of it. You can see this is a very large structure that you can climb up on, and it also has a lot of wonderful kinematic indicators that we can measure right off. Here's an actual image of the faults. The fault was typically covered in grass or colluvium. It was really hard to find, but there were places where we got lucky. This was in a carbonate breccia deposit. We could find these shear zones going right through it. These little sections of rock, these clasts, which are all of the same type. They're all Mandel series rocks, were rotated. You could actually see the rotations inside of here, and you can see that they're separated into an area of rotation and kind of entrainment of rocks. And then over here we find shears and shears over here. So the rocks are clearly moving in a fashion that is what appears to be strike-slip motion. Up here, this was at that fault clip where we believe that the fault contact was, let me go back to it just to kind of show on the map where it was. Oh, here it is. This is a picture of this fault structure right here, located right here. So sorry about that. Okay, and here we see it right here, located cleanly through here. We looked for veins, we looked for any kind of intrusion, anything that we could, baking of the rocks, metamorphic alteration of any of these Paleozoic sediments, and we found nothing. We found no contact aureole, we found no change in the mineralogy at all. The contact was straight as an edge. There was no a class of the metasediment incorporated within the Felsic pluton here. We had no choice but to interpret this as a fault contact right along here. And so we think that we got a very good picture of it. This is the Hustain fault as far as we can tell. Other things that we saw along the fault that are really helpful is we found a lot of monomictic breccias. Here we see this nice big breccia blocks. Here's a pen for scale. Giant blocks that are very superficial. They're cemented by silica cements that are probably precipitated by the groundwater. Here we find another fault breccia where the cements had completely filled in and the cements themselves had been damaged and folded and altered by the fault itself. So this is actually a breccia right here. And this is a carbonate breccia located near a spring. This is a parabreccia, which occurs when there is so much cement being produced that the actual clasts within the cement float apart. So the clasts themselves aren't holding this rock together. This is a giant carbonate sediment that is produced along the fault in one of those areas where the groundwater is interacting with the fault and creating a large spring deposit that is then later on exhumed through faulting. There was a lot of kinematic indicators that we were able to go out and measure, a lot of little folds, Z folds and S folds. Here's a classic example of a nice Z fold that we saw. And here's our interpretation of how this is. This is an image right out of the thesis, but this was just one of many. Here's another fold like this that we detected, and we found many others in the field area. All of these indicate one very obvious conclusion, which is that we see a top-down or bottom-up sense of motion. This is pretty typical of an extensional fault structure. A lot of shear zones were found in the dikes, as well as in a lot of the basement rocks in the Mandel series. Here we see Slickenlines at the bottom of one of these shear zones. Here's a shear zone right here where we see kind of robust, strong rocks. These are ground up, much smaller with veining and clay and definite groundwater alteration in here. But we see it more robust here and here. So this is probably a shear zone, and when we looked at it in detail, we found Slickenlines, and here we see Tom showing the size of those Slickenlines on the bottom of that outcrop. Tools and Slickenlines were definitely the most helpful thing for us to go out and measure, and sure enough, here we find a really great surface off the fault. This is actually where one of the dikes had been exposed along the fault and left really nice tool marks. Unfortunately, we never actually found the tools that left the marks, but we found the marks themselves, and we could definitely indicate or demonstrate that these were a top to bottom sense of motion. So we went ahead and dropped these into stereo nets and recorded all the data of the Slickenlines, and sure enough, we had a nice point where we could say this seems to be the position of the sense of motion on this fault, right here where the blue is. It wasn't the only kinematic indicator we had, though. We also had tensional veins. Tensional veins form when the rocks separate one from another, and as they separate, the groundwater flows in and precipitates either quartz or calcite or something like this, and so you're able to actually measure the orientation of the veining relative to the separation of the rock. And so when we did this, we actually saw on this rock, there's slicks right here on the surface of this rock, and here we see veins, tensional veins, formed as the rocks pulled apart. And we took lots of measurements of tensional veins as well. And what we found is that when we did our stereo net analysis, sure enough, the average posted or plotted right at almost the same position, except a little bit at a little steeper attitude to the Slickenlines. In fact, we also had joints and fractures that we could go out and measure. And here we see the average for our joints and fractures. When we put them all together and we get an average of them, sure enough, the average turns out to be right here. And when you put it on the map, all of those data suggest a perfectly orthogonal separation along the fault between the Mandel rocks and the Carboniferous. So it suggests that this thing is, the fault is moving in a motion down to the southeast. And this would be, by the way, consistent with Eric Collet's idea that we need to go ahead and correct Ulaanbaatar's GPS motion. Once we do it, we actually get exactly the same vector that he got. So we're verifying and validating a lot of his hypothetical analysis. It's kind of neat. But that wasn't the only thing that we saw. We saw that there was definitely extensional motion, a lot of evidence for that. But we also found evidence for sinistral motion, actual strike-slip motion. And one of these was this debris field that we mapped earlier on in the talk. I'm not going to go back to it, but I mentioned that it was offset. And here we find that dike outcrop with the debris field located around it. Here's that dike in image, and we can see some of the debris out here. We would find a zone where there was almost no debris, and then suddenly we would find the debris field again, and it was buried, in this case, to some depth. In fact, it went from a zone of deposition to a zone of active incision. So these are recent drainages that are cutting through here, showing that the debris field has gone from an area of active deposition to an active incising environment. So this is definitely, by itself, a very interesting area to look at. When we went out and measured it, we found a really cool, a really interesting relationship between this clast and this gully. So this was a gully that was freshly cut. It's incising into the terrace deposit. And what we did was we removed this in very, very late at night. And there was an interesting story about a park ranger there, which I'll leave for anybody that has an interest. They can email me about it. But we took a soil sample from underneath this rock, and we used that soil sample for doing optically stimulated luminescence. And we got a date on when that clast was deposited into that offset debris field. And the date comes up at about 6,000, between 4,000 and 8,000 years. So it's definitely Holocene in age. And there's, as we can see here, probably about 600 meters of offset, maybe 500, depending on how you want to reconstruct this over. 500 meters of offset since in about 5,000 years. Now that might not make a whole lot of sense in terms of slip rates, but it depends on really how you interpret this offset. Is the offset fit right over here? Is the offset reconstruct over to here? That's something that a lot more research needs to be done on. But one of the things we do know is that enough offset has happened where there's an area where we see no clasts and we see a change in the depositional environment, one of deposition to one of erosion in the offset debris field. So those are important things to take away. We should definitely take a stronger look at what's going on there. Okay. All right, so we kind of have established, at least on the surface, that the fault is active. It seems to have an extensional component. It also seems to have a sinistral component. They both seem to be playing out. But the other part of the study that we wanted to do was to look at the earthquake recurrence curves in the area and to figure out if the Hustain fault might pose a significant risk. And so what we did was we looked at the earthquake maps, we counted the earthquakes that had happened over the last century, and we were able to develop a curve for a 200-kilometer search radius. In fact, the equation for that curve is located right here. And we get a nice straight line when we look at these things. And in fact, we can plot the recurrence interval for a given earthquake in number of years per earthquake. So the way you read this is the number of magnitude 8 in the area. You read up here, and you realize that one should happen about every 2,500 years. That's not insignificant, that you would be getting earthquakes that often. In fact, I took the liberty of going over here and figuring out how often a 10-year event would happen. Well, a 10-year event, one that you can expect to happen every 10 years, or a 10% chance of happening in any 100 years is actually the better way of looking at it. It's a 5.1. The 100-year event is a 6.3. And so a 6.3 is a very sizable earthquake for that region. Of course, the 500-year event would be a 7.1. I would argue very strongly that the Hustain fault probably takes up a large amount of that risk, that the risk lies on that fault. Between a 500 and 1,000-year event would probably occur along the Hustain fault. This is where we get that evidence from. When we put together the seismogenic thickness versus the rupture length, and we're able to come up with a moment magnitude from published sources, the Hustain fault is quite capable of rupturing 100 kilometers. If we take the seismogenic thickness of the crust in Mongolia to 20 kilometers, which is completely reasonable, it's not unlikely to get a 7.6 magnitude earthquake on that fault. In the case of, let's say that only half of it moves, about 50 kilometers, you're still looking at a magnitude 7.2 to 7.3 on a 10 kilometer seismogenic thickness estimate. So between a 7.2 and a 7.6, these seem to be really reasonable numbers for what the Hustain fault can do. And so when we look at that, we recognize that the Hustain fault falls into this nice region from 7.1 to 7.5, and probably is the largest risk for major earthquakes to Ulaanbaatar, and in fact it's located right in Ulaanbaatar's backyard. So what are the conclusions we can take from this? I know it's a long story, a lot to be said, and I only covered just the very crust of what what we learned in the study. But the Hustain fault is likely a reactivated late Paleozoic thrust that was separating the Mandel series rocks, which are probably accretionary wedge deposits, from the Carboniferous, the Devonian to Carboniferous aged Basin fill rocks that came in later on. The fault plane was probably then intruded by Permo-Triassic granitic plutons, called the Stitch Complex, followed by a swarm of Cretaceous dikes. So a lot of igneous stuff happening during the Mesozoic. After a period of tectonic quiescence during the early Cenozoic, probably the penaplanation that we see across Asia is what led to this absence of rocks. The region underwent extension, and which reactivated the Hustain fault as a normal fault. So it began to rip apart this old fault, this old Tuul fault, as it's usually called in the literature. Topographic analysis of the Hustain ranges indicate that the Hustain fault may be a listric fault, controlling formation of half grobens atop a large detachment fault. So there's a big regional structure underlying the entire area. I believe that there's tremendous evidence for this, and I think that we, as geologists in general, need to go out and kind of ascertain what the real structure is that's controlling what the master structure that underlies all of these things are. The extensional vector ascertained from kinematic data is coincident with much of the Trans-Baikal extension to the north. So it seems to be related strongly with what's going on at Baikal. But Baikal itself seems to be a after effect of what's going on down in the Himalayan orogeny. It's also a sinistral structure. So it's got extension and it's got left lateral offsets on it, from the granites, the rockfalls, and the breccias. The OSL date suggests the offsets have occurred since 7,800 years ago. So it's been active throughout the Holocene, and we see that it's blocking groundwater in the alluvial aquifer. I didn't get the chance to bring this up, but it's also stressing young calcite crystals in that para-breccia that I mentioned earlier. We actually see 2 V's of up to 8 degrees. Which most calcite structures or calcite crystals are uniaxial when you look at them under thin sections. These are biaxial because they're so stressed out from the fault stress building on it. The fault, which exceeds 100 kilometers in length, can produce a 7.2 to 7.6 magnitude earthquake, and it possesses a major seismic risk to the urban areas of Ulaanbaatar. This cannot be ignored. This is an extremely important takeaway. And the kinematic data supports the model of Eric Calais and his collaborators' 2002 paper that the regional GPS measurements, including the movements on the Hustain, are affected by post-seismic stress from the 1905 Bull-9 and subsequent earthquakes. In fact, our data completely has the same vector. It's right on with what Eric Collet found. He predicted this in 2002. Our 2006 put it right on that trajectory. So this cannot be ignored. More measurements of other faults could come in and actually verify what his hypothesis was on this. I've had a few email conversations with him about it. He's very interested in these results himself. I want to take a quick moment and say special thanks to the Mongolian University of Science and Technology that hosted us and our research team and introduced us to the fault in the study area. This was an amazing experience for everybody involved. We want to say thank you. The American Center for Mongolian Studies and the U.S. Embassy in Ulaanbaatar, who actually provided funding as well as a lot of assistance with moving and shipping stuff from the mainland part of the United States back to Mongolia and back and forth, as well as giving us advice on everything from culture and customs to where is a good place to get a hamburger in Ulaanbaatar. Thank you very much. Carl Lippo, who actually provided the OSL dates from California State University at Long Beach, and Jill Peltzer at UCLA, University of California at Los Angeles, who provided us with the satellite images that were used in this study. So with that said, if you have any questions, I know this is a long conversation, or long discussion. If you have any questions, post them in the comment section down below in your YouTube, in the YouTube window, and I will try to get back to you as soon as I possibly can. Thank you for sitting through this very long talk, and if you have any questions, please contact me. Thanks.